I want to talk to you about one of my favorite subjects and one of the sort of reasons this class continues to be a required course. It's really one of the primary courses in which we teach students about how to understand assessing the performance of computer systems. And so we're going to start that today, and it will be a recurring theme throughout. When we talk about computers and we say, well, what computer is the best, or maybe what computer is the fastest, it's not a very simple question. The work that's done by a computer depends on what the purpose of that computer is. Right? So if you have a scientific or engineering workload, then the performance of the machine on floating point operations may be the most important factor. If you're doing software development, maybe integer arithmetic is really important, or string processing may be really important, and so forth. So what is performance? I like to say that performance is meaningless. The definition, this is Merriam-Webster, I think. The definition of performance is doing something. That's what performance is. And then there's this ill-defined notion number 4 there of performance is the ability to perform. Well, we all love circular definitions. The Oxford English Dictionary defines this a little bit better as how well someone or thing does something. And that's the kind of performance we're talking about, right? But we need to know how to measure that how well part. If we don't have a metric is a description of what you're going to measure in order to make a comparison. You got to have a metric for performance. The metric that you choose to use will depend on what's important for your assessment. For a computer system end user, a lot of times what they care about is the responsiveness of their computer system. For a single program, how long does it take from start to finish? For a single action, how long does it take before you get a response from the system? And this is called response time, the time it takes for a response, or it's called latency. In a network, we talk about latency a lot. So on the right side, you see that latency is time divided by one work unit, right? So the amount of time it takes to complete one unit of work, whatever you've defined as your useful unit of work. For someone who's overseeing lots of workloads being executed at the same time or concurrently, they want to squeeze the most performance out of their computer by getting the most number of jobs done in a fixed amount of time. And the generic term for this is throughput. Throughput is the number of work units you can complete in a given amount of time. In a network setting, we usually call this bandwidth. So the number of bits or bytes that are transmitted over a network in a given amount of time. Throughput and latency, historically, these are the two really important metrics for computer system performance. More recently, we also care a lot about mobile computer performance with respect to battery lifetime. So you want to be able to balance the throughput and the latency of a mobile device while also maximizing its battery life. Battery life is measured in terms of energy consumption. So a battery stores energy. Energy is joules. So energy consumption is joules per second, which is watts, which is power. So power is the depletion of energy. If you can only work on one thing at a time, then latency and throughput are multiplicative inverses of each other. In general, when you can work on more than one thing at a time, your throughput is greater than your average, the inverse of your average latency. So let's take a look at what that means. Suppose you have a lunch buffet and you've got 5 entrees. If each person takes 2 minutes for each entree, then the latency it takes to pick your 5 entrees is 10 minutes, right? If you can only have one person in the buffet at a time because the stations are closer than 6 feet apart, then there's no overlap and your throughput is 1/10, right? You've got one work unit completed, which is filling up a tray every 10 minutes. So our throughput is in terms of trays per minute. So how do we increase our throughput? We build a pipeline. We spread our buffet tables out so that we can have our individuals going through in a pipeline. One person at each station, we're now overlapping our work units. So the work being done is one tray every 2 minutes, right? Every 2 minutes, someone completes the last station. And so our throughput is 1/2. Are we done squeezing the most performance out of this as we can? We can use parallelism. We can work both sides of our buffet simultaneously. And so now each station is providing 2 people access at the same time, and we've reached a throughput of 1 tray per minute. Hard to do better than that without crowding people in at the same table. So we can improve performance by improving our response time or our throughput. If we make our CPUs faster, it's usually helpful for both. If we add more CPUs, it almost always helps throughput, but sometimes it hurts latency. And in general, computer architects historically have sacrificed response time in favor of throughput. So we say that some machine A is n times faster than some other machine B if this equation S for speed up equals the time of B divided by the time of A. Sometimes that'll be written as performance of B or performance of A. What it means is the time it takes B to do some piece of work divided by the time it takes A to do the same piece of work. So time of B over time of A equals n. This is speed up when n is greater than 1, and we'll call it slow down when n is less than 1. And then we can say that machine A is S minus 1% faster than machine B. So we take the speed up and we subtract 1 from it, we multiply it by 100, and we can slap a percent sign on there, and that's where we get the term faster than. So this is going to be your Swiss Army knife of performance analysis, speed up. We're going to use it heavily throughout this course. If your time on A is 10 seconds and your time on B is 15 seconds, what's your speed up? 1.5. Very good math. So A is 1.5 times faster than B. We can say A is 50% faster than B. A program is made out of machine instructions. Execution of a program follows the fetch, decode, execute cycle. So the hardware knows about instructions. It's got no clue what programs are, generally speaking. Within an instruction, the hardware further breaks this down into processor cycles, and it typically makes progress on an instruction over multiple cycles. 500 megahertz processor core runs at 500 times 10 to the 6 cycles per second, and it has a cycle time of 2 nanoseconds. 2 gigahertz processor runs at 2 times 10 to the 9th cycles per second. Remember, mega and giga are SI prefixes for 10 to the 6th and 10 to the 9th. So we're just expanding out those SI prefixes. 1 cycle is 1/2 of a nanosecond on a 2 gigahertz processor. Remember that nano means 10 to the negative 9th. Cycle time, which is related to the processor frequency. So this equation is an equation that you're going to want to become comfortable with and familiar with. It's called the iron law of performance. It's existed for a long time, handed down to us. It says that we should measure the performance of a processor by measuring the time it takes to complete a program. And we can break that down into the number of instructions in the program, rather the number of instructions executed during the program's execution. So this is related to code size, but it's not related to the size of the code in the file. It's related to the number of instructions that a program has to execute to complete its work. So instructions per program multiplied by cycles per instruction. This is normally going to be abbreviated as CPI. Cycles per instruction is how many processor cycles does it take for the processor to finish each instruction. This may be given as an average number over all the instructions, or it may be given as a different number for each class of instruction. So it may take you a different amount of time to complete an add instruction as a multiply instruction. So your add CPI may be 1, and your multiply CPI may be 4. It may take 4 cycles to complete a multiply instruction. So then you would have to decouple this equation into different instruction classes in order to actually crank out what the answer is. And then time per cycle, that's the processor frequency. So that's usually fixed by the processor implementation. So the cycle time is determined by the fabrication technology. So how quickly the transistors can switch their state, and then by the architectural design, really the microarchitecture, so the implementation of the processor elements, which is really about the circuit design and how they kind of fit together. Sometimes you'll see this written, this last part written as divided by the frequency, the processor frequency. Since the cycle time is equal to the inverse of the frequency, you can just do a divided by the processor frequency. I like this formulation with the multiplications. Makes it easier to see how things divide out, right? Instructions divide instructions, cycles divide cycles, and you see you have time per program if you divide out the terms units. Reminds me of doing chemistry, like dimensional reduction. Anyone getting nightmares, let me know. The goal of performance is to minimize the time it takes to complete the program. It's not about minimizing the individual terms within that iron law equation. A common mistake is to focus on one of those terms and reduce it. So focus on reducing the number of instructions it takes to complete a program. Maybe you combine an add and multiply instruction into one instruction that can do addition and multiplication together. But then doing that increases the cycle time of your processor. Well, that would not necessarily be good, because you're reducing one term and increasing another. When you multiply them through together, you have to see what the result is, right? So the terms are related to each other. You will almost certainly come across some other metrics. One is called MIPS. Sometimes you'll see this as something IPS. It's millions of instructions per second. So it's your instruction count divided by execution time multiplied by 10 to the 6th. That's where your million comes into play. You can also see it written as the clock cycle time divided by your cycles per instruction times 10 to the 6th. Again, the 10 to the 6th factor there is from the M part, and then the other part is calculating how many instructions per second are completed. M flops, I think we'll talk about that in another slide, but it's millions of floating point operations per second. So just focusing on the floating point instructions specifically. These metrics are problematic. They've been used in the past. They still get used sometimes, but they're problematic. So if you look at MIPS, consider an example where you have a processor that doesn't have any floating point hardware. And a floating point operation may take 50 instructions to emulate in software using integer arithmetic on the exponent part and on the mantissa part, and then bringing that back together. But that takes a lot more time than if you have hardware support to do that. Maybe it's only a single 2-cycle instruction to do this floating point operation, right? So adding floating point hardware increases the number of cycles per instruction, because now you're executing a 2-cycle instruction, so it's going to take longer instead of running single cycle instructions. 50 single cycle instructions have a CPI of 1. One 2-cycle instruction has a CPI of 2 cycles per instruction. Your instructions per program decreases because you replace each floating point operation of 50 instructions by 1 hardware instruction, right? So you go from each time that floating point operation needs to be done, you're reducing the number of instructions executed by 49 instructions. And the total execution time decreases because you're going to get done quicker. So your time per program is going to improve. So by your iron law, you're doing better. But your millions of instructions per second is worse. And that's because you're executing fewer instructions to get the same job done. So this is one of the fundamental problems with MIPS. MIPS gives a benefit to being lazy and executing more instructions that have a lower cycle time. So MIPS ignores the program. It's often been used to quote peak performance, so your maximum MIPS achieved. Peak performance is also a bad idea. Maximum performance almost never matters except in a negative way. Nobody cares what your max throughput is because throughput is, by its very nature, an average kind of metric. You're looking at how much work you can get done over time. So what matters is that you can sustain that throughput over time. Maximizing latency is bad. Maximizing the inverse of latency is good, right? Maximizing your response time is not good. Minimizing it is good. So latency is good to look at in a maximum sense, but only inverted. Peak power is important because you want to avoid it. MIPS is okay to use if you're holding the instruction set and the program constant. If you don't change the number of instructions that get executed and you don't change the program, then it's fine. So if you have the same compiler, same instruction set, you run the same binary, but you run it on 2 different pieces of hardware, this can tell you something about the difference in how those 2 pieces of hardware implement the same instructions. This is really uncommon to actually do in practice. Something flops, you'll see this as sometimes M flops, G flops, you may even see T flops. So megaflops, gigaflops, teraflops. By the way, SI prefix G is actually supposed to be pronounced giga, giga, giga. But in computing, for whatever reason, historically, we say giga. So I'm going to stick to precedent and say giga. Now that I've said it, I'm going to be like 1.21 gigawatts. I need that video here, right? Oh.
Electrical, but I need a nuclear reaction to generate the 1.21 gigawatts of electricity. 1.21 gigawatts!
Oh, at least in the graduate classes, most of the students get that reference still. As I get older and grayer and lose more of my hair, my references become more and more dated. M-flops is the number of floating point operations executed by the program divided by how long it took them. And then you divide out the 10 to the 6th in order to get it into the mega format. If this was gigaflops, you would divide it out by 10 to the 9th. If it was teraflops, 10 to the 12th. So this, again, has the very similar kind of drawbacks as MIPS. It assumes that the floating point operations are independent of the compiler and the architecture. It is a useful metric when you're looking at code generation for scientific and computationally intensive workloads. Use time as your metric for making performance comparisons. Be careful when you read performance results, because if the details of how those performance numbers were arrived at are not given, then you don't know how to get those numbers and you don't know if they're valid or not. And then beware of anything that reports peak or maximum numbers. Usually maximum is important to understand the limits of something and whether a computer system is able to meet its constraints. It's not usually needed to evaluate how well a computer system does its job. There's a subtle difference there. The difference between being able to do a job and how well you do the job. And guess what? Both of those fall under the same word performance, because performance is meaningless until you put a metric on it. So machine A and machine B, we're going to go back to our, got a little keyholing. You can't read that. That's my terrible handwriting. What is wrong with me? Machine A has a clock cycle of 1 nanosecond, a CPI of 2 for some program X. Machine B has a clock cycle time of 2 nanoseconds, a CPI of 1.2 for the same program X. So which of these two machines is faster and by how much? So they have the same program X. We'll assume that it's the same instructions, the same instruction set, and really specify that. We don't need to know how many instructions in this program, so when we plug into our iron law, we don't have to know. Clock, what did I say? I said clock rate is equal to the multiplicative inverse of frequency, right? So what does that mean, multiplicative inverse? It means that the clock rate is 1 over the frequency. So if my clock rate is 1 nanosecond, I want to find the answer to that equation. You just swap their places in that first formulation, right? If the clock cycle is equal to 1 over the frequency, then the frequency is equal to 1 over the clock cycle time. 1 times 10 to the negative 9th in the denominator, 1 over 1 times 10 to the negative 9th is 1 times 10 to the 9th. 1 times 10 to the 9th. Well, 10 to the 9th is the SI prefix for giga. So that's 1 giga, and the units at the end is hertz. So 1 gigahertz. So with a 1 nanosecond cycle time, the frequency is 1 gigahertz. What's the clock frequency, the CPU frequency, if the clock cycle time is 2 nanoseconds? The frequency is 1 over the cycle time. The cycle time is 2 times 10 to the 9th. So it's 1 over 2 times 10 to the 9th. Well, you've got to separate. You can separate that out with the distributive law. 1/2 times 1 over 10 to the negative 9th equals 0.5 times gigahertz. Okay, 500 megahertz processor and a 1 gigahertz processor. Which one's faster? We have to apply our iron law because it does depend on the CPI. How many cycles you can execute in a second is as important as how long it takes or as how much work each of those cycles is getting done, right? The performance of A, or the time of A, is equal to the n instructions per program times 2 CPI times 1 second per cycle. So our clock cycle time. So the time of A is 2n. The time of B is n times 1.2 CPI times 2 seconds per cycle, so 2.4n. 2.4 is more than 2, so 2.4 is taking longer. So we'll put the bigger number on top to get a speed up. The speed up of A with respect to B is 1.2. So A is 1.2 times faster than B. And then we can take that 1.2 minus 1 and multiply it out by 100% and say 20% faster. Speed up is a unitless number. Usually we'll write it as 1.2x faster. That's usually how you'll see speed up written. And then to get it to a percentage, you drop off the 1. It's a little weird sometimes because like if your speed up is 4.2x, then you would actually say it's 320% faster, which is a little strange. So when you see speed up numbers greater than 2, they usually get written as speed up and not translated to that percent faster. When you start saying something is more than 100% faster than something else, it starts to get really a little bit confusing. What's the break-even point between the two machines in terms of CPI? If we have CPI of B is 1.2, what CPI does A need to be in order for them to be the same? Well, we can plug and chug in the same equation. Now we're just going to solve for CPI of A by plugging it in as an unknown in our iron law. So we want our speed up to be 1 because speed up of 1 means that they are the same. When time of B over time of A equals 1, we got the time of B equation and the time of A, and we solve for CPI of A and we get 2.4. So A would have to have a CPI of 2.4 for them to be identical performance on the same program. Here's a similar question. If the clock of B is 2 and the CPIs of A and B are 2 and 1.2 respectively, what does the clock of A need to be? Well, again, you can plug and chug that as well. So the clock of A would need to be 1.2 nanoseconds for them to have a speedup of 1 with respect to each other. So here we've got a table that describes an instruction mix of a program. So suppose 43% of the instructions executed are ALU instructions and they take 1 cycle. 21% of the instructions executed are loads and they take 1 cycle. 12% of the instructions are stores and they take 2 cycles, and 24% of the instructions are branches and they take 2 cycles. Should we implement an improvement to reduce the store cycle time by 1? So change it from 2 cycles to 1 by slowing the overall processor clock speed by 15%. Plug this into our iron law by expanding out the CPI using these weights. So think of these frequency percentages as weights. If the weights all add up to 1, we're figuring out a weighted average of CPI. Take the frequencies as weights and the cycle times. I omitted the ones. So 0.43 times 1 plus 0.21 times 1 plus 0.12 times 2 plus 0.24 times 2, right? So we're just taking the 2 columns and we're multiplying them together. And that gives us an original CPI of 1.36 for this instruction mix. So the CPI, if we reduce the store instructions from 2 cycles down to 1, we shave off 0.12 CPI, right? So it's 1.24 CPI with this enhancement. And then we have to account for increasing the clock speed by 15%. We'll do that by multiplying in our speed up equation the clock speed by the old clock speed times 1.15 will be the new clock speed, right? Because 15% more is 1.15 times the old number. The t's, the base time of the cycle time, is going to divide out. We don't actually have to know what the original cycle time is. We just have to know that we slowed it down by 15%. So the old CPI of 1.36 divided by the enhanced CPI of 1.24 multiplied by the slower clock speed of 1.15 is 0.95. So that means the speed up with this enhancement is 0.95. That's actually a slowdown. So we would not want to implement this, all else being equal. Changes in compilers can also be fit in this by looking at how they affect the number of instructions that are generated for a given program. And so we can use this to look at whether proposed enhancements should or should not be adopted. In the ideal scenario, you would know exactly what program the computer would run and you would use that. In general, we don't know what programs a specific computer is going to run ahead of time. Those workloads are varying and they change over time as well. If you don't have the real programs that are going to be run and you don't know what those real programs might be, then instead what computer architects and compiler designers and computer system performance assessors in general have done is to use benchmarks. Selected program or set of programs that are used to measure performance. There's several kinds of benchmarks. The best benchmarks are real programs that are representative of real workloads. Another really common approach is called a kernel or micro benchmark or synthetic benchmark. These are fragments of programs. So kernels are really popular in scientific computational mathematics kind of workloads. So you take, and that's where the name kernel comes from. You take the kernel of that computational workload and you extract that out of the program, and then you build a little benchmark around that kernel and you see how well does your computer system crank out results for that kernel. You could construct a synthetic benchmark for a file system that just opens files, writes a byte, and closes the file. It's not a real workload. And then instruction mixes, which aren't really benchmarks, and we already saw them, is a table what a representative program executes. One of the more common, prolific, especially historically in computer architecture benchmarks, was the SPEC benchmarks, System Performance Evaluation Cooperative, SPEC. So SPEC's been around since the 80s, the late 80s. Over time, they evolved their benchmarks in order to try to better characterize the performance of computer systems. As computer systems evolve, we want our benchmarks to evolve as well. Newer benchmarks come out in order to help evaluate the performance of computer systems on workloads that are increasingly important. So the rise of web commerce in the .com era motivated the addition of web transactions and transactional processing benchmarks. The multi-core era in the mid-aughts motivated multi-threaded, multi-programming benchmarks. The era of GPU processing and machine learning has motivated those kinds of benchmarks in more recent years. Benchmarks are not without their own problems. Here are some of the really common pitfalls of using benchmarks. So you may choose a benchmark that's not a representative benchmark. It's not a useful benchmark. If the expected workload of your computer system is I/O processing, then evaluating the computer performance using the SPEC integer benchmarks is worthless because they have almost no I/O in them. Using old benchmarks is a no-no. Compiler vendors, hardware vendors, they may optimize their system in order to better execute a specific benchmark because they know that the benchmark suite will get used in order to evaluate the performance of the computer system. And so if they can get a higher number than their competitor, then they may sell more units than their competitor. So they have a profit motive to game the benchmark system. Modifying the benchmarks. So benchmarks are useful because they are repeatable, reproducible. You can compare your results with other people's results. Once you tinker with the benchmark, then your results are no longer, strictly speaking, comparable with other results. Now a topic, middle school math or something. So we've got two machines, machine A and machine B, and they run two programs. So we no longer can use our iron law because we don't have time per program. We've got times for programs. So how do we combine results? One approach would be to take the total time. Machine A takes 1001 time units. Machine B takes 110 time units. So the speedup of B with respect to A is 9.1x. B is 9.1 times faster than A. Correct? Well, misleading maybe. We can use the arithmetic mean and we get the same result as that total amount. Remember the arithmetic mean? When you think of average, you usually think arithmetic mean. Sum up all the times and divide by the number of runs. So the arithmetic mean of machine A is 500.5. The arithmetic mean of machine B is 55, and we get the same 9.1x. So the arithmetic mean and using the total runtime are only valid if the programs run for the same number of times. If the programs are used in different proportions, then the weighted arithmetic mean can be used. So if you know how much each program is going to be run on each system, then you can weight how much each contributes to the arithmetic mean. Sometimes this is a normalized weighted arithmetic mean, normalized meaning the weights all add up to 1. When the weights all add up to 1, you can drop the denominator. You no longer need it because the sum of the numbers from I equals 1 to n that all add up to 1 adds up to 1 by definition. So 1 can be gotten rid of. So suppose you drive for 30 miles per hour for 10 miles and then you drive 90 miles per hour for the next 10 miles. What is your average speed? Quick, this is a quiz. No, I don't, I'm kidding. If we were in class though, I would totally make you do this like a quiz. Like, I'm glad we got that answer. It was a trap. See, the high pressure situation is designed to make you turn off your critical thinking skills. When you're driving a total of 20 miles, but you're driving 30 miles per hour for a longer time than you're driving 90 miles per hour. So our actual average speed is 45 miles per hour. Thank you for playing, though. I was really glad to see that. You get an A for participation, which is really, in life, more important than being right much of the time. Rates don't play well with the arithmetic mean. So when you're averaging things that are specified as a rate, x per y, if you want to average two things that are x per y, you cannot use the arithmetic mean to do that. You can expand it out like this, or you can use the harmonic mean, which is this formula. The harmonic mean is equal to the n number of things that you're averaging divided by the sum of their inverse rates. So we would have 2 divided by the sums of 1 over 30 and 1 over 30 and 1 over 90. So 2 over 1 over 30 plus 1 over 90. Combining the terms, you get 2 divided by 4 over 90 equals 90 times 2 over 4. And then you can divide that out and you get the 45 miles per hour answer that we expect. So the harmonic mean gives us the right answer when we average rates. Now for ratios, another common trick in computer performance evaluation is to use a ratio of performance in order to compare something to a baseline. So here again, we have our two machines, machine A and machine B, same parameters as before. We can take the ratios with respect to machine A as a baseline, so we can divide everything out by the time it takes to run on machine A. Machine A takes 1,000 time units to run program 2, so machine B's ratio for program 2 is 100 divided by 1,000, which is 0.1. Okay. If we take the arithmetic mean of these ratios, which is the wrong thing to do, by the way, we get 1 as machine A's performance and 5.05 as machine B's performance. And so we would say B is 5.05 times faster than machine A. If we take the ratios with respect to machine B, we divide program machine A's run times by machine B's, and we can see that on program 1, machine A is 1 over 10, so that's 0.1. Program 2 is 1,000 divided by 100, so that's 10. And when we take the arithmetic mean of that, we see that machine A is apparently 5.05 times faster than machine B. Clearly, they both can't be 5.05 times faster than each other. So again, the arithmetic mean is the wrong thing to use with ratios. So when you have ratios, you can use the geometric mean, which is given by the nth root of the product of the ratios. So here's the formula. The geometric mean of B with respect to A is 1. The geometric mean of A with respect to B is also 1. So they have actually the same geometric means. Remember earlier on, our arithmetic mean of our total runtime told us that machine B was 9.1 times faster. And the geometric mean says they're the same. The total execution time of the two machines is equivalent only if that shorter program, program 1, is run 100 times more often than program 2. So the geometric mean ignores sort of the weight of each program in some sense. If you're presented with time, rate, or ratio, you should have some sense of which kind of mean you should use to compare them. And when you read a paper and it tells you it took the arithmetic or geometric or harmonic mean, you should be able to look at that and think, is that the right mean to use and why? So performance is meaningless without a metric, and time is the only meaningful unit or metric in life, really. Latency and throughput are our primary high-level metrics that we like to look at. Throughput tends to dominate. Speedup equation is the old thing divided by the new thing, or the unimproved divided by the improved. That should give you a number greater than 1. If it doesn't, then you did not make an improvement. And then when you average numbers, make sure you use the right average depending on what kind of number you're looking at. And the best results will come from using non-normalized numbers based on time metrics.